Thank you all for standing by and welcome to our webinar entitled Understanding the Performance of Cascading Waterways in Ohio Agricultural Landscapes. This webinar series called Freshwater Science highlights Ohio Sea Grant and partnering scientists every month. Every quarter is a different focus from human health and fish farming to harmful algal bloom and human decision making, bringing applied research to the public on issues that affect our Lake Erie communities. I am Jill Gentis-Benicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Dr. Steve Lyon from The Ohio State University. Dr. Lyon's research uses innovative approaches to characterize hydrological processes and engage people across scales to improve resource management. He works at the intersection of water chemistry and hydrometric observation, often leveraging geographical information systems, remote sensing products, and geostatistical approaches. Dr. Lyon came to Ohio State in 2019 as an associate professor of hydrology and water resources and is the associate director for the School of Environment and Natural Resources within the College of Food, Agricultural, and Environmental Sciences at the Worcester campus. We are delighted to have Dr. Lyon here today to talk about his harmful algal bloom research initiative research. But before we do, just a few logistical mentions as we get started. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:20, I'll conduct a question and answer session. If you'd like to ask a question during the presentation, please feel free to pull up that chat feature at the bottom of your screen anytime during Dr. Lyon's talk, and I'll collect and pose your questions out to him at the end of his presentation. As a reminder, this webinar is auto-captioned and is being recorded to be posted on our website for later viewing. Also, we'll post a webinar survey in the chat feature toward the end of the half an hour. Please take a few minutes after the webinar to fill out that survey. It will help us continue to bring you great webinars. So without any further delay, I'd like to introduce Dr. Steve Lyon, presenting Understanding the Performance of Cascading Waterways in Ohio Agricultural Landscapes. Dr. Lyon.
Thank you, Jill. Thank you for that introduction. Thank you, everyone, for joining online. I know it's always fun to sit and eat and listen to one of these things, so I'm glad you can make the time to come and join. Today, I'll talk about some cascading waterway work that we're doing in my research group here at Ohio State University, trying to figure out how these conservation practices work, how they don't work, how can we improve them, how can we manage those. So I'll overview a little bit what cascading waterways are for the Ohio context, and then also layer in some of the research that we've been doing and that we have coming up in the next couple of years as well. So let's get going. So just to start with, if you're from the Midwest or if you've driven around Midwestern landscapes or Ohio specifically, you probably know what a grass waterway is. This is NRCS practice 412. So these are, you're driving past a corn or a soybean field and you see a strip of grass kind of running down the hill in the center of that field, right? These are erosion control conservation practices that have been around for a long time. So primarily, if you think about an erosion process, a rill or a small gully forming in this field on the left, a grassed waterway would then be a practice by going in there, setting the grade and the contour of that and establishing some grass year round, help hold that soil in place to slow the water down as a conservation practice, primarily targeting, erosion prevention practices. So what cascading waterways are, then it's just an augmentation or an addition to those traditional grassed waterways that we would see across Ohio. And so here's an image of one from Allen County. So you can get a feel for how these things look. So what cascading waterways do is this top view here. In this traditional grassed waterway setup, they establish ponds or retention basins, pools, as you will, within the flow of that waterway. So these ponds here, then seen in this image as well, in the bottom part of the figure, are trapezoidal in nature and oftentimes range between 3 to 4 to as many as 5 consecutive ponds, retention basins along this grassed waterway system. The idea being that as water flows and accumulates along the grassed waterway, these retention ponds will fill up with water. And then the first pond, the uppermost pond in the flow, holds water as it spills over, it cascades like a waterfall down to the next one, down to the next one, down to the next one. So this idea of cascading reservoirs is what these are built from. These are a relatively new practice to the state. They've been around for going on the order of 7 or 8 years by now, 2019 or so like that for some of the earlier ones. Um, and there's not that many of them built across the entire U.S., right? One of the first ones built was in Maryland. And so a lot of the practice is coming from that initial designs. And we're at the kind of frontier of how do these things, are they built? How are they designed? How do they work? Primarily, they're targeting like a 10-year retention sizing for a storm event, right? That's the idea for the design. But then the question becomes, what's the efficacy of these practices? How do they work in reality? How are they working in terms of not just runoff prevention, the erosion prevention from the grassed waterway sections, but also the potential for water holding capacity and nutrient retention as we think about things like harmful algal blooms or nutrient load reductions through a conservation practice. Showing some more image of these types of waterways. So they come in many shapes and sizes. And that's kind of the tricky part of the work that we're doing is trying to characterize how do they work, how do they look, how can we make them the most effective they can be. Again, so here this bottom image here is from Allen County in the northwestern part of the state. That's the same waterway that we saw previously. However, this is after a few years of operation, right? So they don't look pristine all the time. So understanding how this type of a system would look and work. Then here from the Dara site in Defiance County, if you're familiar with that, a very, very small cascading waterway with just 3 retention basins, 3 ponds that you can see off into the distance here. And then in Seneca County, another one, a short one, at the demonstration farm in Seneca County, showing another 3 consecutive ponds in the system. But again, very different conditions throughout the seasons and very different conditions across different sites. So trying to characterize these and understand them from a perspective. These retention basins in the cascading waterways primarily can range in size from anywhere, if you think about it as the footprint of a small car, up to maybe the footprint of almost like a school bus in terms of their size. So they can be quite large, or they can be rather small. So trying to get a feel for these systems. And that's really what we've been working with over the past several years now, or back to 2023 or so, from some harmful algal bloom research initiative funding, so HABRI funding, from the Ohio Department of Higher Education. We've been establishing monitoring across several cascading waterways in the state. So primarily the things I'll show today will focus on these 4 locations, Allen County, Defiance, Williams County, and then Seneca County, where the stars are located here. We have constructed cascading waterways that are on the order of 5 to 7 years old at this point. And again, seeing how these things look visually, you think of a grassed waterway system, right, with these retention basins along them. So again, here's that Allen County site looking before construction, Seneca County site during or before a rainfall event, that Williams County site looking at how it would look as rain is falling, as they're starting to flow water through the grass waterway into the retention basins, into the receiving ponds, and then that Defiance County site after a rainfall event. So you can see, imagining these ponds are filling up with water during rainstorm events, and then slowly releasing water through infiltration processes and evapotranspiration processes as well. Okay. So what have we been doing? We've been monitoring these systems, and we've been monitoring them in a couple of different ways. One of the primary ways we've been looking at them is literally trying to measure the water levels in the retention basins, right? How much water is in the basin? When it rains, does it go up? How fast does that water go down between rainfall events, right? We're interested in the infiltration processes. Are these systems actually infiltrating water into the ground, or are they holding water like a pond and not releasing it down in the ground? One of the major mechanisms we want to see happening in these systems is that infiltration, the movement of water into the soil. And so we're trying to monitor that by monitoring the volumes and the depths of water in the systems. We're also grabbing water samples either manually, as the postdoc is doing here, or using auto samplers and things like that. So we're trying to monitor how these systems are working across different seasons and rainfall events. And so some initial results, or some results from one of the sites, just to get a feel for how these systems work in general, right? So we have a cascading waterway at Williams County. It has 3 retention basins in order. And we can see here, these flow from basin 1 is the green line, basin 2 is the blue line, down to basin 3, which is the lowest one in the system, is the orange line. What we show on this graph here is a time series of data. These are observations of the height of water in the retention basin, so those ponds. But then it's translated over to the volume of water using the geometry and the structure of those retention basins. All right, so let's track, for example, basin 1, the uppermost retention basin in the cascading waterway, the first one water would see along the waterway. So the red line here shows 100% filled at capacity. This thing is full of water overflowing. We can see that throughout most of the spring and period of time, very, very wet system in this 2023 data set. And during these largest rainstorm events here, moving into July and August, we see this starts to rise up rapidly and overflows, goes over 100%, right? So what does that mean? The system is actually flowing water out of that retention basin. Maintains a really high level for a while, and it recesses back down. Let's take a look at basin two, the blue line. Slightly different response, but has that same overflowing period in that same window of time. Basin three, same thing, right? Big event starts to overflow as well. What we see when we look at this type of data is basin one tends to fill up and respond first, cascades down to the basin two, which has a delayed response, which fills up second, overflows second, which cascades down to basin three, which overflows last, right? And rarely ever actually exceeds its volume because this system has been designed to maintain flow or to maintain and hold that water back. And so we only see that the system fully flows out the bottom, out the outlet of the last retention basin during the largest rain events for this period of time. These two orange peaks that go over that red line. So the systems are holding water. That's great. If we look at how fast water goes down during non-rainfall periods, what I call the recession, or that ability to infiltrate or move water out of those basins, if we average across all these basins in this period of time of observation, we get about 12 millimeters of loss of water per day across each of those basins, those ponds, right? Well, where's that water going? It can either go up to evaporation or down to infiltration. Daily evaporation for this site is around the order of about 3 millimeters, so a little bit of water every day. So we can't explain all 12 millimeters of water with just evaporation. So it's probably going into the ground. So infiltration is a major mechanism by which water is leaving these retention basins, which is a good thing because that's what you want the water to do. You want it to infiltrate into the ground to slow down that movement and to help retain it into the system. To put these numbers into context, 12 is a number. If we were to look at the Maryland Cascading Waterway, where there's been some published research on before, which is much sandier soil than we'd have in the northwestern part of Ohio, they see about 40 millimeters of water loss per day. So our numbers are smaller, but still a number, right? We're still having infiltration be a major mechanism here. So that's a very good positive result here, seeing that these systems are indeed cascading, meaning when they're designed correctly, they will have water spill over, and they're infiltrating water between rainfall events. All right, so what else have we been working on? We've also been looking at more at an event scale and the inflows and outflows for these systems. So not just kind of monitoring how much water's into the basins during rainstorm events and after rainstorm events, are they working? But what happens to the flow of water through the system? How much comes in? How much goes out of the entire system? How much runoff? How much water is retained throughout maybe a growing season or a year? How does that translate over to concentration changes for nutrients like nitrogen and phosphorus? And then how does that translate over to potential load reduction, right? Because that's what we really care about as a conservation practice. Can the cascading waterways add value to nutrient load reduction in addition to sediment retention and things like that of a traditional grassed waterway? And so we have event-based low flow flumes here shown in the picture with auto samplers are trying to trigger on whenever water flows hit peaks and throughout various samplings and seasons. At the outlets of the systems, then we have weirs, V-notch weirs here that are also doing the same thing with auto samplers connected and routing water into grabbing them so that we're pulling water out and grabbing that sample and recording the flow associated with those numbers. So we're having, kind of instantaneous measurements of how much water is moving through the system. And we grab water samples for subsequent chemical analysis to see what the composition of that water would be in terms of nutrient concentrations. All right, so some event-based responses that we've seen so far for these systems. Here, for example, for a early spring event in 2024, on this graph here, we have these blue dots, which would be the flow coming into the system. So that flume measurement, kind of the inflow at the top of the cascading waterway. You can see a rainstorm event happens. These blue dots go up, some type of a delay and another response. So we have water flowing into the system, right, for value. And we've measured that and monitored that. For this rainfall event, though, no water left the system. The triggering never occurred at the outlet. So all the water in this 1.27 inches of rain that came for this March event were retained in that cell. We didn't see any overflow out the bottom of the waterway. Right. So again, these systems, when designed correctly, are designed to kind of hold all that water in their retention basins, in their cells. So again, here at the bottom is a summary of that in numbers. Almost 14,000 total gallons of water coming in, none leaving the system with for 100% water reduction. That peak flow about 151 gallons per minute. That's peak flow up here. Again, down to zero outflow. So then reduction in peak flows as well. We also see on this graphic then here the chemistry overlaid as well. So concentrations, going on the right axis here, for total nitrogen, total phosphorus and phosphate. So the orange and the yellow, these dots here that enrich the event scale. So that first phosphorus flush as we'd expect, then it dilutes back down. And then total nitrogen being the pink, nitrate, the grayish color, and then ammonia being the green, ammonia being very low in these systems. Total nitrogen up here with a dilution pattern as we'd expect. And then about half of that coming as nitrate, again, with a little bit of a dilution coming through that system here. So very event-based responses as you'd expect. Dilution of nitrogen on a peak, enrichment for that phosphorus thing. So we can kind of see these concentration changes throughout an event as well. And we're monitoring these. We're also grabbing water samples from the basins to see how much of the basin mixes during an event and things like that. So those are things we're always trying to characterize as we look at the concentrations of water through the systems. Another event, then a little bit of a larger event later in the season. Not all events obviously have 100% retention of water. That would be crazy if they were that effective, right? And so sometimes we'll see that events do translate through the system, obviously when the system's almost at capacity and a large late season rainfall event comes through, as this August event came through here for Defiance County. And then we have, when water does leave, it does actually retain some of it, right? So we have a 24% reduction in the total volume. So a quarter of the water actually got retained in the system. Whatever space is there to hold the water holds the water. And with that comes a dampening, a reduction of 20% in that peak flow, as you'd expect. For this same system, then where we see water actually translating through, not all being held in the basins, we actually see a shift in the chemistry as well, looking at the event scale chemistry concentrations. So it's primarily on the nitrogen side of things, not on the phosphorus side of things. And that's what this graphic here is showing. So this is that same event here with the chemistry, with the total nitrogen is the red on the inflow on the left, and then total nitrogen is red on the right here, the outflow. So the kind of drop in concentration for flow. Nitrates as well drop across these two things. Phosphorus levels, though, we don't see that same kind of shift. So here, these are averaged out or shown over on the right-hand side for this event. Again, nitrates showing about a drop in about half in the concentration, and total nitrogen dipping down as well from what flows in terms of concentration to the system versus what flows out. So there is some chemical change in the water that we see. Is that a dilution effect because of the basins mixing, or is that a denitrification effect? It's probably a little bit of both. Because as we're going through the system, we're picking up water that's been sitting there, mixing that, and moving that to the next basin as well. So there would be denitrification processes that could be happening between rainfall events. Let me pick up. Phosphorus, we don't see that same thing. We see kind of constant concentrations across the inlet to the outlet for this, and we're looking more at this in detail to see if we see any differences across the basins, and we see kind of a flat response. So what comes in is what goes out. So it's primarily not changing or altering that. We do see sedimentation, of course, so that will be a question as to how much of that sedimentation could impact the phosphorus concentrations longer term. Something we'll look into in the future. Okay, so then thinking in terms of load estimations, we've been monitoring the inflows and the outflows and the concentrations in moving through the systems. We're also looking at the concentrations in those retention basins, right? And we're also looking at the concentrations of runoff. So we have runoff collectors that are passively accumulating water that runs off of the agricultural fields surrounding the systems. So looking across on this image here, total phosphorus in the top left, total nitrogen in the top right, phosphate in the bottom left, nitrate on the bottom right. Orange bars across these sites. Orange is always the runoff, water coming off of the agricultural landscape directly from the farm field. The bluish color then would be the concentrations from grab sampling in the retention basins themselves. So we can see significant differences across almost every constituent. Some of them are not significant, but vast majority, significant differences across both phosphorus species and nitrogen species for all the sites when comparing what comes off that farm field versus what we see in those basins. So as that basin sits there, right, we obviously have a concentrate, we have a sedimentation happening and a denitrification happening. So we're losing concentration in that system. And that's with mixing as well. So we have some chemical reactions happening as well. So we're trying to characterize these load reductions, what comes in terms of mass of nutrients versus what gets transported and moved through the system. And so that's what we've been working with. And we have these reports then on this. So we're looking over the entire calendar year now. So we're kind of taking that event scale. And we're also taking some in-between observations as well and doing the magic math of let's average this out and multiply this together. So again, we're looking at loads now. So concentrations of the nutrients times the amount of water carrying the nutrients as well. And we're looking across one calendar year. This is 2024 data. And we're seeing reductions across all the sites that we have here, ranging from the 60s up through like the 99% reduction in loads here for total phosphorus, phosphate, total nitrogen, and nitrate. Again, reductions on the order of 80% or so up to like 90% for nitrate. So these are driven primarily by water retention. Those cells hold water, right? We've seen this. The ponds fill up with water as it rains. Biggest rainstorm events, then it does flow over. So in those biggest events, you have load leaving. But during the systems where the water is all retained in the cascading waterway, if flow goes to zero, load tends to go to zero. So we have major reductions in retention in those systems. So these numbers are on par with what has been seen for other sites. So these systems are working very effectively, it seems, for what they're designed to do. We can put those numbers into mass retention as well. So these are pounds for nutrients. But more importantly, we can take that pounds and express it as cost effectiveness. So pounds per dollar, dollar per pound of retention. And so going through that math and thinking about the variability in cost, these things cost $10,000, $75,000 for construction value, not including design, bringing that design number in there a little bit. You can get some back of the envelope estimations. We're putting it in the realm of about $90 per pound of phosphorus retention, $10 per pound of nitrogen retention, which puts them on par with some of the other existing conservation practices you might think of for Northwestern Ohio in terms of nutrient retention and design. So based on our initial calculations for this 1 year of data, right, we have numbers that are in that right ballpark to make these seemingly realistic, cost-effective conservation practice. So we're happy with that. That's great. We love that. We love that. So it's a great take home here. So we see that for our first cut of analysis and what we're looking at for these cascading water systems in Ohio, infiltration seems to be significant. They're putting water into the ground, which is what they're designed to do, which is good. There was initial concerns about that because of the clayiness of our soils. Water is being retained. That volume is being held back, which seems to be a primary mechanism by which they reduce load. And then those nutrient loads are being reduced primarily, right? So that's where we're at with this analysis. What comes next? That was just 1 year of data for a lot of this, right? We've extended this out now. We've got 2.5 years now under our belts. We're analyzing those, trying to look at the impact of weather variability. If you remember 2024, it was quite dry for most of the year. So we had really big reductions in that year because it was quite dry. So anything that did come through could be retained. We're also trying to synthesize across the cascading waterways in the state. So we're trying to bring in not just the 3 we look at, but kind of all of them that exist. There's only about 12 or so that exist across the state that I'm aware of. We're going to go out and start getting some simple assessments of those, trying to characterize how they look, how they're being maintained, trying to put together some guidance around not just construction, but maintenance, longevity, lifespan of those type of things. What are the sedimentation rates for those? How quickly do they fill in? How much do you have to dredge them? Those types of maintenance questions, so we can try to inform a little bit these things and keep them effective going forward. And that is it in a nutshell for what I have to talk about today. Happy to take questions and have discussion. If anything came up and you want to drop me an email, that's my email address again. And again, I'll acknowledge the funding from the ODHE's Harmful Algal Bloom Research Initiative. So, thanks.
All right. Well, thank you, Dr. Lyon. We have some great questions. So let me start off with you had a slide that was it was in the very kind of beginning of your presentation when you were talking about William County's site, and someone had wanted just a clarification that this would be that there was no tile drainage in that area. Is that correct?
That's a great question. For that site there can be tile drainage. I'm not exactly sure off the top of my head. So when we design these systems, sometimes there'll be tile drainage in that field, right? And so if that comes in, what they'll do is oftentimes they'll intersect it with lateral tile drainage that runs parallel to the waterway, which is not so uncommon as you build a waterway as well. And so that can improve the flow of water laterally along these systems. But for what we're looking at primarily that surface water conveyance, right? So what comes in at the surface level and what flows through that system.
All right. Another question that we had was the total phosphorus concentration slash reductions appear to be equal to the phosphate to phosphorus ratio. I think that's what he is
Yeah.
meaning. Does that mean all or almost all of the total phosphorus is in the form of dissolved soluble reactive phosphorus?
Yeah, that's a good. Yeah, I think it may mean that. I think what we're getting is because of these ponds' ability to have settling happening. I think we're actually missing some of the sediment that would come in, so we're not getting anything that's suspended on some of those numbers. So that chart you're referring to, I think reference it has that in it. So we're actually getting some already settled water. Um, and so the number could possibly be higher for the actual concentration of the total phosphorus if we actually go back and look at that sediment richness. So one thing we'll do in the upcoming season is we'll go out and we're going to core sediment from these systems and look at the concentrations or the phosphorus on the sediments in those systems as well. Try to tease out more how much of the total phosphorus retention is coming through that sedimentation.
Okay. Um, you had some costs in dollar signs in the very end of your
Mhm.
presentation. Can you clarify again so there was a question about cost in terms of dollars per acre impacted.
Mhm. Yeah, those numbers were normalized by acre as well. Yeah, and so the easiest way to think about it is so we're looking at construction. There's construction costs associated with these. Like, there's going to be a design and a construction cost. So far, all the systems in the state, Ohio Department of Agriculture has basically designed them for free, which is taking cost of design pretty minimal. Then the major cost then is for construction, and it's a lot of it is it's cut and fill, right? And a primary cost mechanism then is cutting enough but having space to fill or to waste the spoils somewhere that's cost effective. And so kind of you got this balance between the cost of digging versus the cost of getting the spoils either locally or trucking them off site if it's a excessive amount. So that's your size calculation comes into play right there. And so taking that cost there, that construction cost, that's kind of our basis there. And then taking the pounds, the load as a function of per unit area for that number there to put them in standard. So we're trying to get them down to a basis to compare with similar conservation practices and cost per unit area there as well.
Okay. Um, we had someone who just wanted to double check. How do you measure the baseline nutrient loading in the system to then calculate the load reduction from the
Yeah.
cascading waterway?
Yeah. So what we're doing, yeah, and apologies for not being clear on that. What we're doing is we're looking at the load reduction inflow to outflow. So we don't know what the load reduction would have been without the system. We're not doing a control comparison here. We're just saying what's the inflowing load versus what the outflowing load is. That's the reduction there. Um, we're not running these as parallel or paired studies where we have a grassed waterway next to it that we're looking at as well. There are some sites where we could do this but it's hard enough to maintain monitoring at a few sites as well. So these are load reductions across the system, inlet to outlet.
All right. Well, and so we had a question asking about specifically the sites. Um, they were wondering if they were installed on private property or are these designated drains under the jurisdiction of a drainage commissioner.
Mm.
They said, I'm not sure if drainage commissioners exist in Ohio. In Michigan, they can levy taxes and complete projects on a county basis. Are these
Okay.
installed upstream of waters of the state? So, couple
Yeah.
questions there. Sorry.
Yeah. I'm not a lawyer, nor do I pretend to be one on TV. On those sites, two of them are on research properties, so they'd be more owned by the state or owned by the county. Two of them are on private farms, and so they are yeah, subject to all the rules that would go along with a traditional grass waterway system. These are not interim practices or approved practices yet, so there's always that classical like, where do they fall in the whole thing? That's kind of the guidance of where we're trying to get to with this type of research is trying to benchmark some of the information to inform that type of policy and directionality for these things.
Okay. We had another question that asked about how have you checked sedimentation so far?
Yeah. Good. Yeah, we poorly. I'll say that. Be honest. That's the easiest way to say it. What we've done so far is we have those ISCO samples that I showed. I'm showing the data on the sediment things. We've ran them through traditional grab our samples, filter them. What's on the filter? Do that classic thing, looking at an event scale. What we will do going forward, and I think this is a better approach, is we will go out now and we're going to survey all the sites, all the sites that we're working on. We're going to try to expand this out to many sites across the state as well. So we'll go across those retention basins and we'll survey them under dry conditions, with a terrestrial laser scanner, for example, to get a good idea of what they look like in terms of their shape and their size and where they're at. And we'll compare that back with the as-builts, right, from a few years back, the engineering designs of what was actually put in the ground to understand that differentiation. So where are they at today versus what they were at 5 years ago, for example. And so get a mass estimate from that, and we'll have a density estimate from some coring. So from that, be able to estimate per annual what the sedimentation rates or what the total accumulation of sedimentation would be. And try to get that for some recommendations about guidance about what does dredging look like? Because one of the questions I always get from people are like, well, how often will I need to dredge this thing? And how fast will it fill in? And I think that's a great question. So we're going to try to get at some estimations of sedimentation rates as well.
Okay. We had another question dealing with evaporation, how you're measuring evaporation at your site.
Yeah.
Was the July overflow related to the full water table from spring or just heavy rainfall events despite the overall drought in recent summers around Ohio?
Yeah. How we're measuring evaporation, we have weather stations at each site that give us the components for energy balance for estimations of evaporation. And I think the number I use at average 3 millimeters per day, I think that might have come from a satellite derived product that we have been working with our state's climatologists on a little bit. So might have pulled numbers from there to be more robust than the weather station, which was hit and miss for us over the period we looked at. Um, then why did this one event overflowing like this? Yeah, we don't have piezometers out there, so I can't tell you where the water table position truly is at. That's something I'm interested in understanding better, is where that water table is at relative to how much are these isolated ponds that are floating above a water table. We do see, for example, to put that in perspective, at the Defiance County site, large cracks as things dry out, as they oftentimes will. So I think these things can have phases of operation. So when they start to dry out, the cracks, the shrink swell of the clay starts to open up. And I think then they can lose a lot of water quickly. So I think later in the year, you can actually infiltrate very quickly. When you're in that middle ground, we have kind of swelled up soils. You can still have those fast responses. So I think they have to go through a significant drying before they shift their phasing. It's my theory. I don't have any real data to pin that one down. So I can't say how much of this is a remnant of water table position versus just the sequencing of the largeness of an event. Let's put it that way.
All right. Another question about numbers here. Could you share your thoughts on the load reduction of nitrogen versus phosphorus?
I can, yeah. So primarily driven by load reductions, in my opinion, and based on the numbers of how we're doing the measurements, and also based on what we've observed, the load reduction is primarily driven by the change in water volume, or the ability to hold water volume back. Okay, so it's gonna that those two processes are equal for both nitrogen and phosphorus. So then what differs? For nitrogen, I do think we see, because these ponds, sit large times with water in them but no movement. So you'll have denitrification processes. So you are lowering your concentration by a mechanism that wouldn't exist for phosphorus. However, phosphorus will have that sedimentation process, which probably would dominate that as well. So for the phosphate, for example, the DRP stuff, the dissolved stuff, just the load coming from the water, whereas for the nitrate, the dissolved stuff there, probably both the load from the water and a little bit extra push from denitrification that could happen between events. So that would be the mechanisms I would highlight as to their total reduction. That depends how much water you can hold back, I guess.
I've got three more questions if you are good with a few more.
I'm good. And I'll remind folks, feel free to reach out to me with email if you want to set up a conversation about any of this. Absolutely. And if you have to leave because you had 12:30, get out of here.
Yes, it is recorded, so people will get the answers. Okay. Another question we had was, can you foresee using AI to help model drought versus normal versus wet seasonal or annual conditions?
It's great. I will say, I can see two things. I can foresee AI to model everything, because that's what AI is supposed to do. Do I believe AI when it models everything? That's another question, right? I'm very old. I'm an old school kind of guy. I like mechanisms and processes. I don't like my boxes to be totally black. So there's probably a balance between understanding what drives the drought, the processes at play here, or the things going forward, versus being able to see beyond the current state of data, which is what the AI would hopefully give us. So trying to not just go into a space where we only believe what the computer is telling, but also interfacing it with our understanding of the physical processes. So
Great
I'll give you
answer.
a long convoluted answer for a question that's a tough one to pin down, right?
Yeah. Do you know, has anyone looked at how the wildlife are using the cascading waterways?
Mm.
They seem like they would provide better habitat for wetland species than grassed waterways.
Yeah, I can be anecdotal about that, and I can speak to it a little directly. Yeah, when we go to these sites, we see deer prints, we see every species you can think of walking around there, and we see birds and waterfowl and things like that happening. So you can anecdotally we see these are like watering holes. Of course, they have more things. We have the number of frogs you get is ridiculous, right? That type of thing. So yes, I think you're absolutely right that because one of the, and talking with some farmers, some of the concerns I have is like, am I going to have a bunch of goose in my field now that I have to worry about? And I haven't seen that happen, like you see with a pond at a golf course, for example. Um, so yes, you do see an uptick, or I've noticed anecdotally an uptick in activity around these systems. That said, they're not being managed for that per se. So we're not, no one that I'm aware of is targeting to increase their ecosystem service provided for fowl or even for vegetation. You know, oftentimes these are still being designed and implemented with traditional grass waterway approaches. We'll seed them as we would seed a grass waterway for engineering endpoints rather than make sure we have a distribution of natives. I was just on a call the other day about this because we're going to build one of these here. Should we put natives into it? Well, there's no standard to put natives in. We don't know what that would look like. So we have to figure out that standard and how that could look relative to what the reality of the construction would look like. And that's oftentimes the problem with these types of things. It's trying to bring those two together. And so yes, there is potential and no one's managing them that way, but thinking about how we can get that stacked benefit would be an important aspect.
Mhm. Last question. What has the farmer, how have the farmers been in terms of being receptive to this practice? Has there been any follow-up that's been needed to address issues or concerns that farmers have raised, such as the ponds may not be draining?
Sure. No, yeah, so yeah, we haven't done, I haven't gone, no one's gone into deep detail on that. So there's been no real, social study on that aspect, or follow up in that regard. It's something we're hoping to do a little bit in the next phase of our project, but of course we won't do a deep social science dive on that. I can tell you the farmers that we would be working with here would be early adopters. So they are all in, right? They're drinking the Kool-Aid from step one type thing. So, because remember, these are not NRCS approved practices, so they're not getting necessarily subsidies and sharing on the cost, but they're getting benefits working with folks like the Nature Conservancy and other agencies interested in this rural action, for example, trying to help cost offset and things like that. For example, we'll build a cascading waterway here on the Ohio State's Worcester campus, and it will have a EPA a 319 grant to help offset costs on that type of thing. And so we're working with early adopters, so they're happy. Early adopters are always looking for it's great. We love it. We love having more ducks in our fields and things like that. And the question though is like, well, how do they feel about it now, 5 years in? And I get an email saying, can I cut down this tree that grew here? And will it mess things up if I do? Will it not mess things up if I do? And the answer is, you can do what you want to. Yes, you can cut that tree down, right? And trying to target in better guidance. It's like do what you want to, right? Trying to figure out a way to answer that question more succinctly, but also more systematically across all the sites is where we're probably at. Because as you can imagine, every one of these waterways I've been to looks different and is managed a little different. When you mow, how do you mow? Do you spray? Do you do nothing? And they're all over the place, right? And it's fun from an ecological perspective to see them all over the place. I think it's exciting, but from an engineering side of things, I'm like, oh my goodness, I have no idea how this is supposed to be going. So that's trying to pin that down a little bit. It's trying to make better recommendations to make more consistency across management to kind of reduce that burden to help increase that adoption would be one of the ideas.
All right. Well, thank you. I think I got through all of the questions. So thank you again, and thank you for staying on for a little bit longer so we can knock those out. So I guess I'll just wrap up then. This webinar is being recorded. I had a couple people just ask me if it was going to be recorded. We'll be sending that link out to folks here with hopefully later on this afternoon. I wanted to again thank Dr. Lyon for his willingness to talk to us today about his HABRI research. This was really an excellent discussion. Thank you so much, Dr. Lyon, for taking the time. I wanted to also remind everyone that our survey URL for the webinar is in the chat feature, so please take a few minutes to fill that out. This webinar series is sponsored by Ohio Sea Grant and will continue next month with Heidelberg University's Nate Manning, who will be talking about a new innovative water quality data dashboard. The registration link is in the chat. Thank you again, Dr. Lyon, and all participants on this webinar. We hope this was beneficial and hope that you'll join us again in an upcoming webinar. Thank you again, Dr. Lyon. That was such a great presentation. Thanks all and have a great afternoon. Thanks again, Dr. Lyon. It's always great to have you on.
Well, it's fun.
Thank you.
Thank you. See you. Thanks, Joe.
Bye.